Welcome back everyone. So today I have picked up another good problem from one of the past FIITJEE AITS papers, and it's a problem of kind of mixture of collision, friction and relative motion concepts are involved, I guess. So let's proceed. First, read out the problem once. The problem states that board A is placed on board B as shown. Both boards slide without moving with respect to each other along a frictionless horizontal surface at a speed v. Board B hits resting board C head on. Everything is shown in the figure before collision and after collision. After the collision, boards B and C move together and board A slides on top of board C and stops its motion relative to C in the position shown on the diagram. All three boards have the same mass, size and shape. It is known there is no friction between boards A and B. The coefficient of kinetic friction between boards A and C is mu k, and we are given four options. So we'll check all the four options one by one. So this was the initial situation. Here it is shown in the figure, and I have drawn here the situation just after collision. As it is said that after collision the boards B and C move together. So basically B and C will have a perfectly inelastic collision. So for B and C initially, let's say this is mass m moving with velocity v, and this was C of mass m at rest. So after perfectly inelastic collision among these two masses will stick and behave as a single mass of 2m, and velocity will be v by 2 obviously. You can easily get this by conservation of linear momentum. So that I have done for B and C, but for A it will remain the same. Why? Because between A and B or A and C there is no contact force. I mean, there is no force along the direction of motion. Obviously there is a normal reaction from B to A and from A to B as well, but that will not affect in the change in velocity of A, right? So as there is no friction between B and A, the velocity of A will remain the same after collision, as if there was, just to make you understand that there was no force which can alter the velocity of A, I have drawn B and C together and A as separately, right? I mean, I have shown a gap here, but there is no gap in reality. A is on B, right? It is in contact with B. So this is my figure just after collision, but it will not remain same, because if you sit on the frame of B plus C, I mean now B plus C will act as a single body. Obviously there will be some relative velocity of A and A will slide on it, but as it is mentioned that A and C will have a kinetic friction, right? There is friction between A and C, so the velocities will change. Then come to this figure. I have shown this figure after a certain instant, where this dotted line was the joining line of B and C, right? And as initially relative velocity of A with respect to B plus C system was rightward v by 2, right? Here the relative velocity will be v minus v by 2, that is v by 2 rightward. So A will try to slip over B plus C in right direction. Okay, so that much thing is clear, I guess. And at a certain instant, this is the figure, and I have marked this length as xr. I have assumed xr as the relative displacement of A over B plus C block, right? Obviously the head, I mean the front of A was initially at the joint of B plus C, so whatever be the length from that joint to the front of A, that will be the relative displacement, right? And the direction of frictions are also very clear, I guess, because A is slipping rightward with respect to B plus C, so friction will act on A in the backward direction, or in left you can say, and on B plus C it will be in the right direction. And these are the accelerations I have shown. Acceleration of A is F upon m, and acceleration of B plus C body is F upon 2m, right? And now I have written the value of F here at any instant, because as you can clearly see that only this portion is having friction. I mean, you can call that this portion is rough and the contact portion between A and B is smooth. So the normal reaction offered by this portion will be weight of this part only, right? So total mass of A was m, it was distributed over a total length of L, and mass of this marked portion will be multiplied by xr, so its weight will be this times g. So that is basically the normal reaction offered by this portion, this rough portion, and that will only contribute to friction. So this will be mu times the normal reaction, this one. So this is the value of friction. I hope it's clear. So now we'll try to analyze the motion of A with respect to the frame of B plus C. Okay, so this was the acceleration of A, right? I have shown it here. Yes, this one was the acceleration of A in leftward direction. And as we are trying to find the relative acceleration, AR denotes the relative acceleration, right? So we'll just reverse the acceleration of B plus C and add it with A. So this one was the acceleration of B plus C in rightward direction. So we'll just add this much of acceleration in leftward direction to get a relative acceleration 3f upon 2m leftward. Putting the value of f, we'll get 3 mu g xr upon 2l leftward. So it's very common that we write A as v into dv dx, right, in kinematics. So all these things have a subscript of r. I am writing this just because to mention that we are analyzing it in the frame of B plus C. So all these terms of acceleration, velocity, displacement are relative. So that small r represents nothing but the relative motion. That's not a big deal. So I have written AR as VR times dVR dxr equals to this. So you just take the VR terms and left hand side and XR terms at right hand side and integrate. So what will be the limits? Now it's initially it was 0 because initially this was the B, sorry, yeah, this one was the B plus C system and this one was A. So relative displacement of A was 0 obviously. This one was the joining line of B plus C and the front end of A was also coinciding with this line. So x, this one was the initial value of xr, that was 0, and finally the situation is something like this. Let's say this is B, this is C, and this is A. So from this line joining, the front end of A has moved a distance of L. So xr at final stage is L. This is my upper limit. So initially the relative velocity was v by 2. I have shown here, oh sorry, I have rubbed it, but initially it was v minus v by 2, that was v by 2, and finally it will be obviously 0 because at that instant we are trying to find, right? It is mentioned in question. Let me mark that line, that board is slides not, yes, here it is, stops its motion relative to C in positions shown on the diagram like this. So when the system is at this stage, the relative motion of A and B plus C block has stopped. So VR relative velocity will be 0. So just putting the limits, we'll get this result, and just rearranging the terms, we'll get the required result that L is equals to V square upon 6 mu G. So that was one option, I guess. Let me mark that. Yeah. So A was one of our answer. And now we'll try to find the next 3 options. At final speed of each board, that you can find very easily by conserving the linear momentum. So this one was the situation just after collision, and this is the final situation. Finally all the boards will move with a common speed. I have assumed it as V prime. So we'll just conserve the linear momentum between these two instants. Initially it was mv times 2m times v by 2, that was the linear momentum of B plus C, and finally all the 3 masses 3m will travel with the speed of v dash. So v dash comes out as 2v upon 3. So B is also true. Now the options are regarding work done by frictional forces. Okay, so let's move on. So the only force that is acting on C during its initial instant, where it was having a velocity of v by 2, to finally it will have a velocity of 2v by 3, is friction. So I can clearly conclude that whatever is the change in kinetic energy on C, according to work energy theorem, that will be the work done by friction on C. So I've just written that only, that work done by friction on C is nothing but change in kinetic energy of C. Initially it was having a speed of v by 2 and finally it is having a speed of 2v by 3. This is its final kinetic energy, this is initial kinetic energy. Subtracting these two will get 7 mv square upon 72, and I guess it was not in the option, so it's not our answer. I mean, the option that regarding work done by friction on C is not a correct one. And another option was regarding total work done by friction. So I am claiming that at every instant the force of friction is same for both the bodies. Obviously these are action reaction pairs, you can call. Let's say this one was the B plus C body and this one is the A. So this one is the F, if here also friction is F. So on both the bodies magnitude of friction is same, but displacement of both the bodies are not same. We have already shown that L is the relative displacement of A over B plus C. So relative displacement is not 0. That means the actual displacement of A and B plus C is not same. And if the force at every instant is same, but the total displacement is not same, so you can easily call that the work done is also different for A and B plus C. And you can clearly see that the direction of friction is opposite in both the cases. So if for any body we will get positive work and for another body we will get negative work by default. So if the magnitudes of both the works are not equal, then after adding these two values we will never get 0. We will get a work done by total work done by friction as some non-zero quantity. So the 0 option was not true. Let me show it here. Yeah, there was 0 given, it is also not true, and mv square by 12 was also not coming. Some 7 mv square by something, right? 7 mv square by 72 is correct answer for this option. So I guess it's clear. I have solved all the 4 options in the same question, and it's a quite interesting problem, I guess. I hope you liked it. Thank you. That's all for today, and stay tuned.